everyone. Today we're going to talk about quantum computing and try to demystify a topic that might be intimidating to a lot of people, but is really exciting and represents the future of what computing might be able to do. Elena, talk to our listeners a little bit about what quantum computing is and why they should care about it.
So quantum's been around for decades, but in the last few years there's been significant advancements to the hardware, and it's becoming much more of a reality than a pipe dream. According to Gartner, quantum will become more of a reality by 2023, which is much sooner than the 20 years from now, which is in most people's thinking. What's also interesting from them is a statistic that 20% of all companies are going to have quantum computing related projects in 2023 versus 1% today. And the possibilities that quantum computing opens in terms of solving really complex problems that are impossible to solve in today's traditional computing is what makes it so appealing.
And what are some of the advantages of quantum computing over classical computing?
So the first primary one is speed. So quantum computing is incredibly fast and faster than traditional computing. And the second is costed efficiency. So think about us being able to simulate on a traditional computer what quantum is able to do, but you need hundreds of thousands of servers, millions of servers in order to do that, where you just need one quantum computer for the right use case.
Okay, all right, great. So how does it work?
If you think of traditional computing as processing with digital bits, ones and zeros, quantum computing leverages qubits. And there's two very important properties that you can't go to a quantum lecture and not talk about. One is superposition and one is entanglement. So I think the easiest way to explain it is through an example. So if you picture a coin and we're flipping a coin, as we're flipping that coin, while it's in the air, it's a head and a tail at the same time.
Okay.
That concept is called superposition. Now, if you introduce a second coin, and we're now flipping two coins next to each other, they're related to each other. They have, let's say, wind exchange or whatever other environmental forces that make
something like that. Yeah.
Exactly, that make them not independent. And the non-independence is called entanglement, where their results are dependent on each other. So quantum computing has superposition and entanglement among a few other important theorems, but those are the most important two that help make it what it is.
So if I have one coin, I can have a 1 or a 0, a head or a tail, right? Which is like a digital thing. If I have two coins, instead of just a 1 and a 0, I have 4 different possibilities, right? A head and a tail and a head, two heads or two tails. And if I have 3, I suppose I get even more, and 4, I get even more. So it enables you to do things, that's how you get to do things much faster?
Exactly right. And if you, not to get deep into the physics, but I think it's important, if you have n qubits with your quantum machine, you can simulate 2 to the n states. So in your example, 2 to the 2 was 4, and 2 to the 3 was 8. In terms of power, it's interesting to note that a 200 qubit machine, in order to simulate in traditional computing, you need more bits than you have atoms in the entire universe, not just Earth.
Okay, yeah, so we're not going to do that, right? So,
No.
okay. So let's talk a little bit about some of the use cases, right? So as you said, this has been around for decades. I first heard about quantum computing in the mid-90s. It was this pipe dream that I'm like, yeah, okay, one day I might have to worry about that. What are some of the actual real-world problems that people are looking at quantum to solve?
So with traditional computing, it's very good at sequential processing. And quantum computing is very good at parallel processing. So in terms of use cases, they're really optimized for the parallel use cases. So something that comes to mind is large-scale optimization. So in financial services, let's say you're trying to optimize a particular portfolio, and you have 12,000 stocks, and you need to maximize the returns based on different variables and constraints within your portfolio. Quantum computing would be very helpful in that sort of use case. Machine learning is another one that comes to mind.
Sure.
So
yeah, sure.
Large amounts of data, trying to find trends within that data. Quantum computing can help, leveraging superposition and entanglement, can look at the data all at the same time. And as long as you're applying the right algorithm to that data, can help you glean insights that would take many thousands of traditional computers today. Specific examples that come to mind, let's say in the agriculture space. So we need to plant crops and we need to maximize our revenue. And there's different light factors and how much rainfall there is and the particular makeup of the soil, let's say. So quantum can help compute all of those variables to figure out what is the maximum plant that you can get in a particular place subject to criteria. So if you start to see agriculture companies all of a sudden buying quantum computers, you'll know why.
Right, exactly. So just carrying that example a little bit further, right? Because you could do a lot of those agricultural sort of things with traditional models and all that, but one of the challenges I think you have is you're going to take the soil samples or whatever, you can't measure everywhere, right? So you're just going to look at one area over here, one area over here, and sort of guess that things in the middle act the same way. Whereas with quantum, instead of doing 1,000 samples, you might be able to do 1 million or 1 billion sort of samples like that and get much more particular about where you do things. Is that fair?
Exactly. Sampling is a great use case for quantum computing.
So why aren't we doing more of this? Why don't we hear more about it? Why is it still so many years away?
So it's a good question, and I think it's really important to note that the end state here is not to get to a point where quantum computing is the end-all be-all in the universe. Okay. A much more realistic state is that quantum computing and traditional computing live side by side. Mm-hmm. We have traditional computing that is very good at sequential processing, and we have quantum computing that's good at parallel processing. In an end state, we leverage both. So let's say a person in the enterprise comes in, they're doing their traditional applications, and then when they need to leverage a quantum computer for a particular use case or a particular example, they can rent that quantum computer like in a mainframe environment or like a cloud environment for their particular application needs.
Kind of like how supercomputers were. It used to only be a handful of companies had them and you'd run out of time, and now they're much more. Right?
Exactly.
Okay, finally, this topic is probably a little bit beyond what a lot of our listeners would have thought about as they think about their environment today. What do they really need to know, right? If you're a business leader and you want to learn more about how this applies to your business, what should they be focused on?
So the first thing is to educate yourself and not get overwhelmed by the word quantum computing and potentially not having a physics background. The goal of introducing quantum computing in the enterprise is not about having everyone have a PhD and become a quantum physicist and understand the nuts and bolts and build the hardware. If you're good at that, there's definitely places to go. But from an enterprise perspective, the goal is leveraging this fantastic hardware and capabilities to the benefit of the business and solving real business use cases. So I would urge business leaders to educate themselves, find use cases that are relevant for the business, and explore how they can improve their business through quantum computing and speed up and efficiency and cost.
Great. Elena, thanks for joining us today.
Thanks.